Hello everyone, we shall begin the next chapter called as ray optics and optical instrument. This would be the first lecture in this chapter. So let's begin. The first topic here is called as ray. Now geometrically, ray would mean it will have a starting point and some direction. This is called as a ray geometrically. In physics, we use the same idea to represent the flow of energy or to represent the movement of light energy. That is because, as seen here in this example, the torch gives out light. If we look at a small region somewhere here, then the entire region will be illuminated. There is light everywhere. Even in case of a light in a room, the entire room would be illuminated. You wouldn't find a dark spot somewhere. So it is practically impossible to draw the entire region always. So to represent this in a better way, we use a ray. So as given here, light rays are nothing but a model explaining the movements of light from one point to another point. Example, imagine there's a window here. So in this case, what you can do is you can just draw a ray to represent the movement of light. We can draw a ray like this. So we can put a source and then we can put a ray like this. So this indicates the energy of the light moves in this direction. So ray is convenient to express the movement of light, and light carries energy. So this direction also indicates the direction of flow of energy. The next thing is to define as to what is optics. Now optics is a branch of physics which deals with studying properties of light and interaction of light with matter. So that branch of physics which deals with studying properties of light and interaction of light with matter is called as optics. There are many instances where matter or light would interact with matter. For example, think of a case where light falls on a mirror. Here it is interacting with matter. Think, for example, light falls on water. So there are many instances where light would interact with matter. So studying those properties is called as optics. That is branch of physics. Now this optics can be studied under three heads called as ray optics. The second thing is called as wave optics, and third part is called as quantum optics. That is because no one knows how light is behaving, because there are two properties to it. It is seen that light exhibits dual nature. A dual nature means light exhibits both particle nature as well as wave nature. We will see what this term is in later chapters. But now understand that light exhibits both particle as well as wave nature. In fact, when matter also in motion. Example, think of electron in motion or proton in motion, or think of some matter in motion. Even those matters also exhibit dual nature. So dual nature is something which is seen everywhere in the universe. But the point is, how does it actually behave? As I told you, no one knows how light travels. Rather, we can explain as to what light could be based on the properties what light exhibits. So we can assume that light may travel like a ray, or light may travel like a wave, or light may wave like a wave function. Do understand here that we are not saying light is a ray. We're not saying light is a wave. We're saying that light exhibits, light shows properties like a ray as well as wave as well as a wave function. This is called as treating light like a wave function. So we'll see them one by one. Under ray optics, we treat light like a ray. Now, based on ray optics, the properties like reflection, diffraction, as well as rectilinear propagation of light can be explained by assuming light to be like a ray. As given here, what is seen here is we have a source of light and light moves through small pinholes. This property of light, the light travels in a straight line, is called as rectilinear propagation. So it means that light travels in straight line. We will see what these properties are. So you might have learned this in school also as to what is reflection, what is refraction. We will take it up in detail in this chapter also. For now, understand that branch of physics which treats light like a ray is called as ray optics. Again, I'm telling you all that it doesn't mean light is a ray. We're just treating light like a ray. The next branch of physics or optics which treats light like a wave is called as wave optics. So under wave optics, we treat light like a wave. Based on wave optics, the properties like interference, diffraction, and then polarization can be understood. Again, we will see what these properties are in the chapter on wave optics. For now, understand that wave optics means treating light like a wave. The third branch is called as quantum optics. Under this, we treat light like a photon. But to be more technical, we treat light to be like a wave function. So that branch of optics which treats light like a wave function is called as quantum optics. Based on quantum optics, we can explain like properties like Raman effect as well as photoelectric effect. In fact, many more properties can be explained treating light to be like a quantum particle or a wave function. This is the latest theory developed. So in class 12 syllabus, there is a chapter on ray optics, which is a present chapter. There is also a chapter on wave optics. So we'll see what this in detail in next chapter. But quantum optics is beyond the scope of this syllabus. Now understand the fact that in quantum optics, we treat light like a wave function. There's no need to go beyond this. Next definition is called as objects and its type. We will define what an object in a minute is, but then this object can be a point object or an extended object. A point object means whose dimension is very small compared with the distance involved. To remember that the idea of point is not the same idea as what we use in geometry. The idea of point is different here. Here point means it's a relative term, which means we compare whether something is a point object or not based on the distances involved. So the object could be either a point object or an extended object. Now objects can be of two types called as real object and virtual object. Real objects are those objects from which light rays actually emerge from the object. That is, for example, if you look at example like a bulb or torch seen earlier, light from this emerges out. So light goes in all direction. So this object is called as a real object. So a real object means the object from which light rays actually emerge. Diagrammatically, we can show as given here. So we can think of a real object like a bulb and then we draw with rays. To understand that in ray optics, drawing rays is very very important. Just drawing lines will not be of any use because it's a ray optics. So keep in mind to draw with arrows also. So this object where light goes in all direction is called as real object. So as seen here, if light falls on this optical element, this could be anything. This could be like a mirror, this could be like a lens, this could be any object. When light falls on it, it behaves in different way. So those objects from where light emerge is called as real object. As seen here, sun is an example of a real object. Even a bulb, a candle burning, these could be examples of real object. Next thing is called as virtual object. Now, an object is said to be virtual if light rays appear to converge. If light rays appear to converge, is called as virtual object. That means that, for example, think that the light rays are converging at a given point. They're trying to meet at a given point like this. Suppose in its path, if you place a mirror like this or something else, then these light rays would reflect or refract. So this point where they would have gone and met, this acts like a virtual object. We'll take up this in detail in the later topics. It'll become very clear from there. For now, remember, virtual object means in terms of ray optics, these are points where light rays actually or light rays appear to meet. So to summarize this, a real object means a point or an object from which light rays would diverge. This is called as a real object. So from where light rays actually diverge is called as real object. Virtual means light rays will appear to converge. So the point with appear to, they actually don't converge, but they appear to converge, is called as a virtual object. As the name tells us, virtual means something which isn't real. It exists only for a certain amount of time. Again, we will see what this is in later topics. It will become very clear from there. Now remember that virtual object means where light rays appear to converge. Next is image and its types. So it is defined as, image is defined as a point of convergence or apparent point of divergence of light rays after they undergo either reflection or refraction. What it means is that in case of mirror, you all might have learnt in high school that in case of mirror, the light rays undergoes reflection. Light reflects and comes out like this. In case of lenses or something which is transparent, light rays undergo refraction. So these light rays after reflection or refraction may either converge at a point. They may converge at a given point, or the light rays may appear to diverge. So based on that, we have two kinds of images called as real and then virtual image. A real image. You all might have learned this in high school. Real images are formed when reflected or refracted rays actually meet at a point. Whenever the light rays actually meet, it's called as a real image. For example, you all might have done this in school, that if you take a convex lens and then if you're able to focus the light rays onto a given spot, if you adjust the focal length, if you adjust the lens such a way that the spot is focused to a single point, then what happens after some time is, because of intense heat from the sun, and since the energy falling on this is focused to a given point, this part would heat up, and after some time this paper starts to burn. So here you can imagine that the dot what you see here, the spot what we get, that spot is a real image. In terms of diagram, if this is like a convex lens, then suppose somewhere here is sun present. Now here what we do is we draw parallel rays. So parallel rays basically means that the object is very far away. In this case, if we draw parallel rays, and you learned at school that a convex lens would converge these light rays. So this point where they converge, you get a spot. So this spot is nothing but the image. So these images can be caught on a screen. A screen doesn't mean the screen what you think of like a material like a cloth and all. A screen means some kind of a medium where we can get an image. The screen could be like a paper, the screen could be a wall, could be anything else. So that's what screen means here. In case of virtual image, it is formed when light rays appear to diverge or emanate from a point. What it means is that if you look at example of a plane mirror as given here, suppose we have plane mirror here. It is common sense that if we place an object somewhere here, an object O, at this point image is formed. Now we'll take some light rays from the object. This light ray falls like this and this ray falls like this, and after reflection these would reflect like this. So even if you place a screen in front of this, these light rays cannot give an image because they're diverging. But if you draw the light rays backwards, these light rays appear to come from a given point. So this point will appear to come from is called as a image point. It's not drawn in proportion here, but get the idea clearly that the distance from here to here will be same. You can try this using pencil and scale because drawing with a free hand on this board is difficult. So this point is called as image point. It's a virtual image. So in case of a virtual image, the light rays appear to emanate, or if you see from this side, if I get this light rays, if you see from this side, it's like light ray coming from the point A. So this is called as virtual image. We'll summarize above study. So if you look at a real object means an object from which light rays are diverging. This is called as a real object. We're studying in terms of ray optics only. It's called as a real object. Now virtual object means use the word appear. So virtual object, it means the light rays appear to converge. So this point will appear to converge is given here. So this point will appear to converge. It's called as a virtual object. In terms of image, if you look at a real image, so real image means it's a point where light rays actually converge. They converge here. So this point is called as a real image. And then virtual image, it means that the light rays appear to emanate or appear to diverge. This is called as a virtual image. So be careful with these diagrams. Learn any one has to be obvious. For example, if you learn about real object, it is very obvious that from a real object light rays would diverge. Now virtual means opposite of it. Since light rays diverge from here, virtual object means they appear to converge. If you know any one, I think could be easily understood. In terms of image, you know that in case of real image, the light rays actually converge, while in case of virtual, it is opposite of it. Since it's converging here they appear to diverge. So make a note of these things and study them properly. Next topic is called as reflection of light. It's a very, very common phenomenon what you might have learned in school also. We'll just recap it here. So it is a process in which a light ray, when incident on a, example, like a mirror or a reflecting surface, then what happens is the light rays would bounce into the same medium. So to define it, we can say it is a phenomenon or a process in which when light ray falls on a surface, it rebounds or bounces into the same medium. That is called as reflection of light. As given here, you've taken xy. Now this xy could be like a mirror, could be anything. We just call xy as a reflecting surface. To generalize this, it's a reflecting surface. Now this AB, this AO is called as incident ray, and then we draw normal. Here normal means it is in mathematical sense. So normal means it is perpendicular to the surface. So here we draw normal at this point O, and then this OB is the reflected light or reflected ray. So this AO is called as incident ray. This is called as reflected ray. The angle which AO makes with the normal, this I, is called as angle of incidence, and the angle which the reflected ray makes with the normal is called as angle of refraction. Remember these few terms. AO is incident ray, I is angle of incidence, ON is a normal, OB is the reflected ray, and the angle R is called as angle of reflection. Do remember that the angle of incidence and angle of reflection are measured only with respect to normal. As seen here, you can see the image of a boy in water surface. This is basically because of reflection. The next thing is to understand about the laws of reflection. There are two laws of reflection. The first law says the incident ray, the reflected ray, and normal at the point of incidence all lie in the same plane. As given here, you can find there is a source of light. Light is falling on this edge. So you can see this edge of this board. Light falls on this board. So this ray is incident ray. After falling from here, the angle what this light ray makes with the normal, this angle here is called as angle of incidence I. After reflecting, this light ray also moves in the same plane. It moves in the same plane only. This would be R. It is not that the light comes out of this plane. So it is not light comes out anywhere like this. It doesn't come out anywhere. It's in the same plane only. That's the first law. It says the incident ray, the reflected ray, and normal at the point of incidence all lie in the same plane. To make it more sense out of it, if you place a glass slab below this, then what you find is you find the same thing here also. You find its reflection here also. So you find that even here also these two light rays are in the same medium. It's the same surface. That is, light comes like this and comes out like this. So even here you find that the incident ray and reflected ray are in the plane of the gas. That's the first law. The second law says the angle of incidence is equal to the angle of reflection. That is, if this is incident ray, the angle what it makes with the normal is called as I. And after falling on this edge, it reflects into the same medium. the angle what forms is called as R. The same way, if you look at this reflection of this whole system, this would be incident ray, and this the reflected ray, and the angle made here would be normal. So this angle and this angle would be equal. For example, the angle made here is say 30 degrees. It means even this also would be 30 degrees. That is the second law. The angle of incidence is equal to the angle of reflection. Now we look at the next kind of mirrors called as spherical mirrors. Now spherical mirror, we'll first define it. A spherical mirror is part of a hollow sphere. It is not that we make a sphere and break it from there. It isn't. Just that we can assume that we can understand that a spherical mirror is part of a hollow sphere. So based on that, we have two kinds of spherical mirrors called as convex and then concave spherical mirror. As seen here in this diagram, we'll assume that only this part is part of the mirror, not the other part. So what you can do here is, if this part is silvered, that is, if the outer part is silvered, then light would fall and on the inner surface reflect. That is, just draw this part of it. It's like this. So these lines means it is silvered, which means it's like a reflector. So those mirrors where the outer part is silvered and inner part is reflecting is called as a concave mirror. So this is called as a concave mirror. You can have a case where the inner part is silvered. If you look at this part alone, if this part is silvered, that is, if inner part is silvered, then light falls on the outer surface and then reflects. So this is called as a convex mirror, something of this kind. So if the inner part is reflecting, it's called as concave mirror. If the outer part is reflecting, it's called as convex mirror. Examples are shown here. Example, look at this case. Here we find that this inner part is silvered. It's called as a convex mirror. In this case, the outer part is silvered. It's called as concave mirror. As seen in case of a spoon also, the spoon has two surfaces. If somebody looks at the face through the front part, then the front part behaves like a concave mirror. If somebody looks through the behind part, then the back part looks like a convex surface. Here some examples are given of concave and convex mirrors. For convex mirrors, the examples are rear view mirrors of vehicles, that is vehicles mirrors, and also you find such kind of mirrors in say big apartments or houses. Even this is a convex mirror. Examples of concave mirrors are the mirrors which is used for shaving or the small face mirrors as shown here or here, and even the dental mirrors as shown here are concave mirrors, and also even the car headlights are like concave mirrors. We'll look at some definitions about spherical mirrors. Now, first and foremost, the part where light reflects. Example, from this to this part, or from here to here, from this part is called as aperture. We call this as say A, B. This also as A, B. So this A, B is called as aperture. Aperture means it is the effective it is the effective reflecting surface. It's called as aperture. It basically means it is that part through which light would reflect. It's called as aperture. The center of the aperture is called as pole. So this point here is called as pole, and this point here is called as pole. It's a printing mistake. This point is called as pole. So pole would be the center of the aperture. That's the first point to understand. We studied that spherical mirrors are part of hollow spheres. So if the whole sphere is constructed, if you had a whole sphere, something of this kind, then we'll have a center of the sphere. So this would be center of the sphere. Even here also, we'll have center for this imaginary sphere. This is called as center of curvature. That is because what we get is not a complete sphere, but only a part of it. We only get a curve. So this C is called as center of curvature. So this P was called as pole of the mirror, and then this C was called as center of curvature. The center of curvature means it is the center of the imaginary sphere of which the mirror is a part of it. That is called a center of curvature. Now, the distance between the center to this point, to the pole, if it was a complete sphere, then the distance between the point C to point P is called as radius. But here, we don't have a complete sphere. Rather, what we have here is only a part of the sphere. In that case, the distance between the pole to C is called as r. This r is called as radius of curvature because we have only a part of the sphere, not the complete sphere. So remember these 4 points. And finally, a imaginary line which is passing through the pole and center of curvature, which is seen here as SXX dash. This line is called as principal axis. It's called as principal axis. It is PRINC PAL, principal axis, AXIS. Next is a very important definition called as focus. Okay, it is called as principal focus here. We'll first define as to what is a focus. So focus of a spherical mirror is a point. Here we're defining principal focus. So it is a point on the principal axis of the mirror at which the light beam incident parallel to the principal axis passes through or appears to pass through after reflection by the mirror. To put in simple language, you can see by a diagram. If you assume that this is like a mirror, since here the inner part is reflecting, this is a concave mirror. And what happens here is, imagine that the object is very far away. When the object is very far away, we represent it by parallel rays. So by drawing parallel rays, it means the object is very far away. Theoretically, it is at infinity. We'll draw few light rays of this. These light rays, after reflection, example this light ray or this light ray, after reflection they would reflect obeying the laws of reflection. And then if we draw it here, then what happens, this light ray after reflecting will pass through a point like this. Same way, even this light ray after reflection would pass through a point. So this point where light rays pass through after reflection, this point here is called as principal focus. Do remember that even here the laws of reflection is valid. That is, for a plane surface, normal is very easy. Drop a perpendicular, that becomes normal to the plane surface. For a spherical surface, it would be its radius of curvature or radius. That is, to understand this, we'll take example of a circle like this. In this case, if this is center of this, say, circle, which is sphere in 3 dimension, at this point, if you want to find the normal, then we draw a radius vector. So this is normal to this point, like this. The same way, if you want to find the normal at this point, again same thing, we draw from here a radius vector. So normal to a sphere would be its radius vector. So in the same sense, somewhere here is center of curvature. So if we draw normal, it will mean going like this. So the angle formed here and here are same. So this point where light rays actually meet after reflection is called as focus. This is for a concave mirror. Now we look at a convex mirror. For a convex mirror, something of this kind. For a convex mirror, the center of curvature is somewhere this side. This will be center, and a line passing through center of curvature and the point P, which is called as principal axis. This is the center of curvature C. This is point P. Again here also, suppose if light rays fall which are parallel, one light ray like this and one light ray like this, by using the laws of reflection, we can show that these light rays at reflection would reflect and go like this. It go out like this, and this comes out like this. So these light rays cannot meet in front of the mirror. So if we draw them backwards, these appear to come from this point. So the point from which they appear to come, this point is again the principal focus. That's why we told earlier that the focus is a point where light beam incident parallel. That's very important because the light ray should be parallel to the principal axis. So these light rays pass through, as given in case of a concave mirror, or appear to pass through, which means they appear to come from this point in case of a convex mirror. So this point is called as focus. The next thing is focal plane. We'll take it from here only. The next topic. Now think of a case where the light rays are not exactly parallel to the principal axis. That is, we have a case where we have a concave mirror, and then we'll consider its principal axis. So this point would be the pole of this mirror, and somewhere here would be center of curvature. Now in this case, imagine that light rays are parallel to themselves, but these light rays are not parallel to the principal axis, which means these light rays would reflect, and again these light rays would meet somewhere, meet at a point. So this point where they meet would be again focus. It's called as focus here also. Similarly, if you look at light ray from other direction, if you look at a similar kind of a concave mirror, and then we look at a principal axis, suppose light rays are falling parallel, but they're falling like this. So these light rays are parallel to themselves but not to the mirror, not to the principal axis. So after reflection, they appear to meet at a point. So again, this point where they meet would be the focus, which means it is seen from here that these light rays, whenever they're parallel, they meet at a point called as focus. Now theoretically, we can have infinite focus points. That is because it is based on the light's orientation. So if you put a plane here, a plane like this, then this plane contains all the possible focal points as given here. This diagram, if you put a plane at this point, then all the focus points will lie on this plane. For example, if light rays falling somewhere at an angle like this, it will meet somewhere here. So light ray falling here meets somewhere here. Light ray falling here meets somewhere here. So it is seen that we get infinite such focus points. All these points lie on a plane. This plane is called as focal plane. The focal plane is a plane which is perpendicular to the principal axis, and this contains all the possible focus points. Out of these infinite focus points, there is one focus point which is very important, and this focus point lies on the principal axis, and that point is called as principal focus. So do remember that principal focus is one of the focus points. Theoretically, mirror can have infinite focus points, out of which the most important is called as principal focus. Therefore, the distance between the pole and the focus is called as focal length. So focal length for a mirror is the distance between the pole and the focus point, or distance between the pole and the principal focus point. The next thing we have here is called as Cartesian sign convention. Cartesian basically means it's like the x, y, z coordinate system. It's called Cartesian system. To make sense out of it, we can think of a concave mirror. Now what can happen is, if suppose in front of the mirror an object is placed like this, say an object AB is placed. We'll take few cases where in one case the image is formed somewhere in front of the mirror like this. We call it as A dash, B dash. Another case, we'll think of a case where the image is formed beyond the mirror. We'll call it as A double dash, B double dash. We can't get two images for a given object. I'm thinking of cases where either this could be an image or this could be an image. There are two possibilities. I imagine that the distance from this point P, suppose imagine that distance from P to B dash is say 5 centimeter. Similarly, imagine from P to here is again 5 centimeter. It is not drawn correctly, but understand the point. Now in this case, you observe carefully, both distances are 5 centimeter, but in one instance the image is in front of the mirror, and in another instance it is behind the mirror. So by just saying 5 centimeter, it could mean any one of the values. To avoid such confusions, we use sign convention. A convention basically means that it is a method, or it is something which we use to make things easy for us. Convention is not a rule, it's not a law. It is only what we make easy for us. It's called convention. In this case, we want to find out such instances, and also observe that AB or A double dash B double dash is erect while A dash B dash is inverted. So again, A, B and this can't have same signs. To avoid such confusions, we use the sign convention. It has 3 points in it. The first point is that all distances are measured from the pole along the principal axis. That is because we need a reference point, and that reference point is the pole. For any system, for any measurement, we need a reference point. So in case of mirrors, spherical mirrors, it is its pole. So pole is the reference point. So distances are measured from the pole. Do remember, the convention is very, very important, because in ray optics the formulas are very simple, but then by putting improper signs the answer will be wrong. So make a note of this. And also later topics also we will use similar notations or similar conventions with slight modifications. We'll see what it is. So this first point is done. Second point is distances measured in the direction of incident rays are taken as positive, and distance measured in the direction opposite to that of incident ray is taken as negative. So to understand from here, in this case the light ray, this is the object AB, so for the mirror purpose the light would move from left to right. This is how light would move. Now to measure the distance between the object to the pole, we start from the point P. We start from point P and go towards point B, because the reference point is the pole. So in this case, starting from point P and going to point B, distance between pole and the object is called as object distance U. It's called as U. So U is called as object distance. Distance between the pole and the image is called as image distance V. It's called as image distance. In case of this object, we're starting from point P and we're going to point B. So we're going against the light. So by this sign convention, PB would be negative. Imagine that this distance is say 8 centimeter, and you can say in this case PB is equal to minus 8 centimeter. The same way, if we look at PB dash, even here also we are starting from point P and going towards B dash in direction which is opposite to direction of light. Even here this would be negative. So this PB dash would be minus 5 centimeter. Now we look at PB double dash. So to find this, we're starting from point P and going towards point B double dash. Now do remember, in all the cases we are starting from P because P is a reference point. So in this case we are going with the light. The light doesn't enter here, but still what matters is the light direction matters. So we're trying to go with the light. So by sign convention, this P B double dash would be plus 5 centimeter. That's the meaning of the second convention. Distances measured in the direction of incident ray are taken as positive, and distances measured against the light direction is taken as negative. The third convention is that distances above the principal axis are taken as positive and those below are taken as negative. In the same example given earlier, AB and A double dash B double dash, these heights are above the principal axis. So these would be positive, while A dash B dash is below the principal axis. So this would be negative. So these are the three sign conventions. To make it more simple to understand, we can think of a convention in the form of an XY system. So XYZ or XY is called as Cartesian coordinate system. In this case, if you look at this, we saw in the previous slide that light was moving from left to right like this. So if this is the pole, you can think of this origin as the pole, then if you're going with the light, in that case the distances are positive. As seen in the previous example, PB double dash was positive. If we go from O in this direction, this is minus x direction. The distances from here would be negative, which was the second convention. So there you saw that distances measured against light direction is taken as negative, which means distances along plus x is taken as positive and distances along negative x is taken as negative. Similarly, if this is the principal axis, that's what it means, then distances or heights above it, which would mean along the positive y-axis, so this heights will be taken as positive, and distances below it, which would mean it is the negative y-axis, the heights would be here negative. So whatever we learned earlier has been summarized as this XY system. So in fact, XY system would be easy to understand and do numericals. Thank you.